All right, we'll get started. Happy something. Let's try this again. Okay. Well, happy Monday, and it's week 6. You have your midterm on Wednesday, so we will see you here. I guess Wednesday morning as well. I will email out a seating chart, okay, so be on the lookout for that. It'll come with a map, so you'll know where to sit. But yeah, that's coming up. So now we are, I guess, in the second half of the course, where we will focus a little bit more on computational statistics and numeric methods, different aspects, I guess, regarding using the computer to help us answer statistical questions. Now, an important concept that we need to cover before we really get into computational statistics and all of that is this concept of floating point numbers, how the numbers that we see represented in the computer, okay, as we use the computer to do calculations, these are approximations. These are approximations of numbers, and they are not actual. They are not what they appear, okay? So we are accustomed to dealing with real numbers, okay? And there are a bunch of kind of definitions and constructions for what exactly real numbers are, but just kind of the intuitive idea is that you have this number line, this infinitely long number line going from negative infinity to positive infinity. The integers are equally spaced out, and then and basically any other point on that line is a real number, right? And you have infinitely many values, and if you pick any two locations on that line, okay, even if they seem like they're really close to each other, as long as you have two distinct locations, there are infinitely many real numbers between those two locations, right? Between 0 and 1, there's infinitely many values. 0 and 0.1, there's infinitely many values. And that's kind of the idea with the real number line. And we have these properties that we are accustomed to having and relying on when we use real numbers. And you learn these properties quite early on, usually with integers in the beginning, but then you just kind of assume this holds for all real numbers. And it does. These properties do hold for all real numbers. So, the associative property where you can do a plus b first and then add c, and it's going to be the same thing as doing b plus c first and then adding a, and then same thing with like multiplication. And then the distributive property where you have a times the quantity b plus c is going to be the same as a times b and then adding a times c, or changing the order. A times b and b times a are going to be the same, and a plus c and c plus a, right? So these are all properties that we're accustomed to, okay? And then, and every real number also has a decimal representation. There's basically, we're saying that any number you select on that real number line, okay, you have this line and you pinpoint any location, whether it's pi or e or the square root of 2 or 1/2, okay, whatever it is, we can represent that with a decimal representation. Now, some of these numbers go on to, have infinitely many decimals, right? So pi is known for having infinitely many decimals, but if we can write every single one of them down, there is some decimal representation. It can't be represented with as far as we know, it cannot be represented with a finite decimal representation, but there is a decimal representation, right? And decimal representation basically means you got powers of 10, and so 5,413.29 is 5 times 10 to the third, 4 times 10 to the second, so on and so forth. Okay, so every number we can represent with decimal. Scientific notation is basically the same thing, except you just roll the decimal point over so that the leading digit, so that you have basically one number in front of the decimal point, okay, and that's the leading digit that's not 0, and then everything else is, stored in there, and then you multiply by 10 to the negative, 10 to the whatever, okay? And it's useful for representing like really big numbers and really small numbers, like, I don't know, Planck's constant and Avogadro's number. These are like really big numbers, they're small numbers, and this is how we represent it. That we call this part the mantissa, and this part the exponent. Sorry, and that's what we have there. Okay, and these two things are equivalent, right? So we can represent 5413.29 as 541329 times 10 to the minus 2. The normalized scientific notation is 5.41329 times 10 to the third, and so on and so forth. And we have these things. Okay. Now, we often represent real numbers and perform calculations using decimal representation. And a lot of numbers do have finite decimal representation, such as the number 1/2 is represented with the decimal representation of 0.5. That's no problem, okay? But a lot of numbers do require infinite decimals to represent them. All of our irrational numbers, okay, have infinite decimal representations. And a lot of even rational numbers, like 1/3, have infinite decimal representations. You just have to go 0.333, and the 3's go on forever. Okay, and so every time you write down a decimal representation of a number that has infinitely many decimal places, but if you're going to write it down on paper, it's going to be an approximation. Okay, and using approximations as substitutes for things that have infinite numbers has I wrote profound implications for the properties of real numbers that we take for granted. Okay, and that's basic. That's the crux of what's going on inside of our computer. So computers are unable to represent real numbers with infinite precision, right? Computers do not have infinite storage, so we use a fixed number of bits. We use 64 bits to represent a number, and this requires that a lot of numbers be represented with an approximate representation. And I can kind of demonstrate like the side effects of this happening. Okay, so I'm gonna play you a little video, okay, that I recorded of me using an old calculator. Okay, and you've probably experienced this as well. I don't know if you've played around with calculators. So the idea here is I'm going to do 10 divided by 3 on the calculator, and if I do 10 divided by 3, this is what I get. I get 3.33333333, right? This is not a surprise to anybody. You do 10 divided by 3, you get 3 1/3, and this is how we would represent this with decimals, okay? Now, if I say, what is 10 divided by 3 times 3, okay? The answer is 10, right? The answer is 10. But when you approximate this quantity of 3 1/3 with decimal, then what happens? When you take this quantity and multiply it by 3, what do you get? You get 9.99999, okay? Now, this is nothing profound, yet at the same time, it breaks a fundamental rule, okay? With real numbers, you would do 10 divided by 3, you get a number, 3 1/3, you multiply that by 3, and you get 10, okay? But here, if I do 10 divided by 3, and I take that quantity and I multiply it back by 3, I don't get back 10. I get something close to it, but it's not 10. It's 9.99999. Nope, that's not what I want to do. Okay. So, shoot. Okay. Another thing. Okay, so that's that. We get 9.999. You know, and okay, and then this is stupid, but on the other hand, if you do 10 times 3, you get 30, and you do 30 divided by 3, and you get 10. Okay, so that's not a surprise, but the fact that changing the order of operations, right, going from 10 times 3 divided by 3, and then 10 divided by 3 times 3, how you get different results depending on which one you do first, that breaks the rules of real numbers, okay? And so if you keep that in mind, that's what happens when you deal with a calculator. So, you know, that eight-digit calculator, you know, it's floating point because it can do 3.333 and whatever. That fact, basically, that same problem exists in your computer. That when you do something like 10 divided by 3 times 3, okay, on your computer, you don't get back something like 10 down. Now, I don't know about that particular example, but basically the same kind of idea where changing the order of operations and things like that break down, okay? Other examples is, here, let me show you this one. If you take the square root, so here I'm going to do 2 square root, and this is our approximation, right, of the square root of 2, and this is a pretty good approximation using, you know, eight digits of precision, okay? However, if you take this number and you square it, which you can do by doing times equals on the calculator, if you square that, you don't get back 2. You get something close to it, but not exactly 2, 1.999998, okay? And of course, if you do 2 squared and you get 4, and you take the square root of that, you get 2. So, but the order of operations changes, okay? And let me just kind of demonstrate this as well. So this is, let me open up R here. All right, so I'm going to store 0.1 as A, so A is the value of 0.1, and then B, I'm going to do the quantity 0.3 divided by 3. Okay. And so I say, hey, what's B? 0.1. But then if I ask, is A equal to B? That comes back as false, okay? And you're like, are you sure? Here's A, here's B. Is B and A the same? It comes back false. What's going on? Okay. Here's another quantity. I'll call this C. C will be 0.1 plus 0.2. Okay. And then so what is C? C is 0.3. And then I'll call D just 0.3. All right. So here's D. So here's C and here's D. Is C equal to D? All right, and we get false, okay? But then if I do other things, like here's E is going to be 0.4 minus 0.1, okay? Here's E. I can ask, is C equal to E? And that's going to be true, all right? So here's C, here's D, here's E. I can ask, is C equal to E? Yes. C equal to D? No. Okay. And it feels strange. It feels like, what is going on? Something doesn't feel right, okay? Okay, here's another example where I make a sequence going from 0 to 10. I say go from 0 to 1 by 0.1. So I get 0, 0.1, 0.2, 0.3, 0.4. I ask, what's the this number here, the fourth value, and it says that's 0.3. And then, okay, and if I say B is 0.3, is this 0.3 and this 0.3 the same? And they're not, okay? And then here's, okay, so I do 4/5 times 3 times 5/4. I get back the number 3. I have 4/5 times 3 times 5/4. I get back the number 3. And again, okay, I've got 3. And are they equal? And again, the computer says they are not equal to each other. All right, and this feels very frustrating. Like, what? How is this, which is clearly it's the number 3 here, and this is the number 3. How are these not the number 3? Okay, and like, just to show you, I'm not making this up. Okay, what letter am I on? Okay, so we'll say F is this. Okay, so F is that, and then we'll say this is G. Okay, so F looks like 3, G looks like 3. I can say, is F equal to 3? That's false, but is G equal to 3? That one's true. So one of these is equal to 3 and the other one's not, and they're not equal to each other. Like, so what's going on? So one thing I can do is I can say options, digits equals 20, all right? And then we can see the difference between all these. So this is A is not 0.1, but it's an approximation. When, remember, calculation for A was, I said this is A, I just typed in 0.1, but guess what? Typing in 0.1 in your computer, the computer is actually not able to represent 0.1. You get this internally, okay? Internally it's stored as this, because it's kind of like asking the decimal calculator to represent 1/3, okay? You can't do it exactly, right? If I ask what's B, or I did 0.3 divided by 3, this is how it's stored internally, okay? So these are not quite the same, okay? And then over here I have C. What do you get when you do 0.1 plus 0.2? You get that. What do you do when you type in 0.3 directly? You get that. So these two things aren't exactly the same. E was 0.4 minus 0.1, and so that's going to be the C and E are equal to each other, okay? F is the number 3, and G is the number 3, and 3 is the number 3, okay? So F, while it looks like 3, if you do 4/5 times 3 times 5/4, that doesn't give you 3. It gives you 3.00004441, okay? Versus G, if you do 4/5 times 3 times 5/4, that comes back to be exactly 3, okay? So this is what's happening inside. All right, so hang on, let me give you your first view quiz answer. Week 6, Monday is D. D as in dog. D as in dog. Okay, and so here, this is just a silly example again. I have 0.3, 0.4 minus 0.1, 0.5 minus 0.2, 0.6 minus 0.3, 0.7 minus 0.4. Okay, with the real number line, all of these values should be exactly the same of 0.3. Okay, however, on the computer, we have 3 unique values. 1, 2, 3 unique values. I don't know. 3 unique values of 0.3. Okay, we have 0.2999999. We have 0.3000004. And then 0.299999993, okay? 3 distinct values. And again, that's frustrating. All right, so what we're gonna do in the rest of today's lecture, and also, so Wednesday you'll take your exam, and then Friday we'll continue this lecture. On Friday, we'll get into how the computer stores numbers, okay? So I guess I could have just ended the lecture and just said, binary numbers, or just like when you use your computer numbers are not the same as real numbers, and we could have just left it at that, and then you would have just gone through the rest of your life wondering like, oh, I hope this works. But we're going to dig down into exactly how the computer stores numbers, and you'll learn kind of like how we represent all of these different things in floating point representation. And it's still a little bit ambiguous in terms of, like, is this going to give me exactly, which value of 0.3 is this calculation going to give me? You still might not know, but I think you'll have a heightened awareness of, when you should use, I guess some of the pitfalls of using a floating point number, okay? And I think, sometimes, I don't know, like on Reddit, there's like these programming and coding subreddits where they show like, these are problems when, people use floating point numbers and they check for equalities and things like that. And on the internet, it'll say like, no, you can't enter this number because it's not allowed or whatever, but it's, things are breaking, all right? Okay, so internally, all of our computers are stored in binary, okay? All information is stored in binary because we have these bits and we can either turn them on or turn them off, okay? And so each bit is a 0 or a 1. And like decimal representation, we're accustomed to decimal representation, and we can represent any number in decimal form. You can also represent any number in binary form. Okay, every number on the real number line can be represented in binary form. It just requires infinitely many digits. And again, the computer, we don't use infinitely many digits. I don't know how familiar you are with binary, but basically in binary, the first place is a 1. The second place is, the first place is the 1s, which is 2 to the 0. And then the next place over is going to be 2 to the 1, so that's your 2s. The next place over is 2 to the second, so that's going to be your 4s. And the next place over is going to be 2 to the third, your 8s. So 0 is all 0, 0, 0, 0, 0. 1 is going to be this. To represent 2, it's 1, 0. The number 3 is 1, 1. 1, 2, and 1, 1. 4 is going to be 1, 4. 5 is going to be 1, 4, and 1, 1. So 4 and 1. So 1, 0, 1. 6 is 1, 1, 0. So a 4 and a 2 and a 0. And 7 is 1, 1, 1. So 4 plus 2 plus 1 makes 7. And then the whole process repeats, except this leading digit gets replaced with a 0. We replace the 0 with the leading digit with a 1. And so this is going to be the exact same pattern. We have 8, 0, 0, 0, or 8 is 1, 0, 0, 0. 9 is going to be 1, 0, 0, 1. So an 8 plus a 1, and 10 is an 8 plus a 2, and 11 is 8 plus 3, 12 is 8 plus 4, so on and so forth, okay? And it keeps going, and you count to infinity using that, all right? So this is how we represent binary, okay? So the number 11 is 1, 0, 1, 1. We have 1, 8, no 4s, 1, 2, and 1, 1, and that adds up to 11, okay? Fractional values, okay, can also be represented in binary, and it's just working in the opposite direction, okay? So in decimal, you have the number 1/2 or 0.5, okay? In binary, that's 0.1, because every place we have the point here, this is the binary point, okay? So every spot after the binary point is going to be a power of 2 to the negative. So we have 2 to the negative 1. 2 places to the right of the point is going to be 2 to the negative 2. 3 places to the right of the point is going to be 2 to the negative 3. So 1/2 or 0.5 is equal to 0.1 in binary. 1/4 is 0.01, okay? And 1/8 is 0.001, okay? That's 1/8, because that's 2 to the negative third over here. And so this number right here is the equivalent of 3/8. 3/8 would be 1/4 and 1/8. So 0.011 is how we would represent 3/8 in binary. Okay, is that okay? And so a lot of numbers that we have just get represented. We'll have an infinite binary representation. So for example, the decimal value 0.1, 1/10, okay, in binary is going to be a repeating binary pattern of 0.0001100110011, so on and so forth, okay? and we would take the 011, 0011 and repeat that off forever, okay? And again, we only have a finite number of bits, okay? We can't store the entire number because that would require infinite storage, right? Like trying to store all infinity digits of pi, you would need infinity storage, which we can't have. Even if you have like 10 terabytes of storage, you would not be able to store the entire number of pi. And so we just say, hey, let's use 64 bits. That's a lot. And we get something that's an approximation, okay? And so we have this, we get an approximation to the value, and this is why 0.1 plus 0.2 is not equal to 0.3. And that's because when you do the binary approximation of 0.1 plus the binary approximation of 0.2, you don't get the binary approximation of 0.3, okay? So, similarly, if I did on the calculator, if I did 1/3 plus 1/3, I would get 0.6666666. Yet if on the calculator, if I did 2 divided by 3, I would get 0.6666667. Okay, and I would say is 1/3 plus 1/3 equal to 2/3. And on your regular decimal calculator, they're not equal to each other. And basically the same kind of problem is happening here. All right, so in floating point representation, how do we store our numbers? Okay, so the electrical engineering organization, okay, they came up with a standard for how we're going to represent floating point numbers on a computer. And so this is a standard, and basically all computer chips these days adhere to this standard. I guess before this standard, computer chips might represent numbers in different forms, but this is going to be the standard. And so we'll look at this from 1985, and then which was the standard created in 1985. They revised it in 2008, which basically just clarified a few more things, but we're going to just kind of study the original. I guess the 2008 just kind of expanded on it a little bit, but we'll just study this, okay? And you can read more about it. IEEE, the 754 standard for floating point representation, and this is how we are going to use it, okay? And so all of the numbers in that we store, okay, will be stored. We will store our values in basically scientific binary notation, normalized, okay? So that means we have a sign bit, okay? -1 to the s, so either 0 or 1. So if it's a positive number, s is going to be 0, and if it's a 1, s is going to be, our number is going to be negative, okay? And then because it's in normalized scientific notation, the leading digit before the point is not going to be a 0, right? So we're going to have we're going to just assume the leading point in front of the leading value in front of the point is a 1. If it's not 0, it has to be 1 if we're doing binary, because we only have 0s and 1s. Okay, and then we have all of these. We call these the mantissa bits, okay, or the significand, right? So these are all of our bits. And then it's going to be multiplied by a power of 2 to the n. That's going to be our exponent. Okay, so we are going to store these 3 components: the sign, the m digits of the significand, and the exponent, n, okay? And the leading one before the dot, which we call a binary point, is not stored in the computer because it's implied for it to be 1 for all numbers. If it would be 0, it's no longer in normalized scientific notation. Okay, let me give you your next view quiz answer, which is the letter A. A as in apple, A. Okay, so let's say we wanted to take this number, 6.375. So this is 6 3/8, okay? And in decimal, we have 6.375. In binary, this is represented with the 6. Like if I just converted this straight to binary, I would have 1, 1, 0. That represents our 6. A 4 and a 2 and 0 makes 6. And then 3/8 is a quarter plus 1/8. Okay, so I have 1, 1, 0 for the 6 point, no halves, 1 quarter and 1/8. And that would be 0.011. So 110.011, and that would be 6 3/8, 6.375. Okay, if I want to represent this in binary form on the computer, okay, what I would have to do is I have to normalize this. So I take that number 110.011, and to put it into scientific notation, I move the binary point over 2 spots to the left. Okay, so now I have 1.10011, and I'm going to multiply that by 2 to the 2nd power. Okay. Is that okay? Yeah, question?
How would you like represent the 0 if there's always going to be?
Yeah, that's a very good question, and so that's going to be our next lecture on Friday. But yes, if there's always a leading 0, you can't represent, and leading 1, you can't represent the number 0. So the engineers are aware of that. So they included how do we represent 0 in scientific notation, or in this binary form. Okay. Okay, so we have 1.10011 times 2 to the 2nd power, and so this, if you look at this directly, this would be 1 plus 1/2, no quarters, no 8ths, plus 1/16 and 1/32, and that's 1.59375. And then if you multiply that by 2 to the 2nd, or multiply that by 4, you get 6.375. So it works. That's our equivalent value there. Okay. So that's basically how we would store these numbers in the computer. We would eventually we would store 0.10011. We would store the exponent. We would store a sign. Okay. Now, how we do this is depends on how many bits we are using. And so in R, all of our floating point numbers are double precision floating point, and that's why it says type double rather than just float. It's type double to indicate that it's double precision floating point. Double precision means we use 64 bits to store a number, and the 64 bits are budgeted in this manner. We have 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa. Okay. In other languages, you can also specify single precision floating point and long double. And so single precision has fallen out of favor just because our computers are so powerful. But if you go back a few decades, computer memory was very limited, and using 64 bits to store a number felt like a luxury. So you'd use half of that, and you would get less precision in your number. Okay, but it'd be good enough for a lot of kind of your simple applications and things like that. Okay, and then in other cases you can have even more precision, long double, and so on and so forth. Okay, sometimes you'll see things like sensationalized articles about how NASA only uses 16 decimal places of pi or something like that, and it's true, and that's because we use double precision floating point, which is approximately 16 decimal digits. Okay, and so when you do calculations, 16 digits of pi is good enough to get you to the moon. Okay, and most of your calculations don't need that, right? So pi is, I don't know, we have these contests for figuring out all billion digits of pi, and really 16 decimal places is probably good enough for most applications. Okay, so that's what we have. So this is kind of, I guess, a picture of what you can see. So we have bits 0 through 63. So that's our 64 bits. And we use 1 for the sign, 11 for the exponent, and then this will be our mantissa or our fraction. Okay? And so that's what we have. Okay, so regarding the exponent, we have 2 to the 11. We can represent up to 2 to the 11 or 2048 unique values, okay, with our exponent. So we have 11 bits here, and so that you can have, each one can be a 1 or a 0. So how many unique values? We can have 2048 unique values represented in our exponent. 2 of these integers are going to be reserved for special cases, okay? So we set aside 2 of these, so that leaves us with 2046 values to represent positive and negative and 0 exponents. And so what we do is we allocate about half of them to be positive, 1023. One of them will be 0, and the other 1022 will be negative. Okay, so the integers in this range, going from negative 1022 to 1023, we basically shift all of our values down. So basically the 2 integers that are all 0s and all 1s are reserved for special cases. So the smallest number that we'll have is a 1, and then the largest we'll have is 2046. And we offset these numbers with a bias of 1023. Okay, so if our exponent is this, which is equal to 2046 in binary, this represents the integer 1023. We take this number 2046 and subtract off 1023. And then this number, which represents the number 1, we subtract that bias of 1023, and this represents the number negative 1022. Okay, so we're taking this range 1 through 2046, and we're just going to slide the whole thing down 1023 values so that we can represent negative values and positive values with our exponent. Okay, and so this bias is called, the exponent bias has a value of 1023. And basically the way you can calculate that is you can take the number of bits that you have, 2 to the 11, subtract off 1, okay? 2 to the 10, and that will give you 1023, and then you subtract 1 from that, and that gives you 1. I'm sorry, 2 to the 10 is 1024, subtract off 1, you get 1023. Okay, so this is, if you count all of the values, we have all 0s is a special case, and all 1s is a special case. These are the 2048 values we can represent. And then starting at 1 all the way up to this number, we just offset by 1023. Okay. So the special case of all 1s is used to represent either infinity or nans. Okay. And then the special case where the exponent is all 0s, this puts us into a different mode called the subnormalized or denormalized mode. And when we are in subnormal or denormalized mode, then we have a different set of rules that will allow us to represent values like 0 and other small values. Okay, and in that case, the non-stored leading number is going to be a 0 rather than a 1. And that will get covered on Friday's lecture. All right, so to kind of explore this a little bit, we're going to work with what I call a mini float representation. So it's going to follow the same rules and principles of the IEEE 754 binary representation, but here I'm going to only use 8 bits, okay? And they are going to get allocated as 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. This is going to give us a very kind of limited number range, but it's going to follow all of the same kind of principles that the big double floating point does, and basically all of the same kind of implications and ideas that apply for the big version also apply to this. It's just to a smaller number range. Okay, so 1 bit for the sign, 3 bits for the exponent, 4 bits for the mantissa. Now we have 8 bits. And that first bit is going to be the sign bit. So if it's a positive number, the sign bit is 0. If it's a negative number, the sign bit is a 1. Okay? And one side effect of this is that you have two representations of 0. You have a positive 0 and a negative 0. But it's 0. Okay? We have 3 bits for the exponent. 3 bits for the exponent means we have 8 unique values that we can represent. Again, all zeros is a special case. All ones is a special case. Okay? So that leaves us with 6 values that we can represent. And again, half of those values will be positive, 1 will be 0, and then the remaining will be negative. So we're going to be able to represent in the exponent values anywhere from -2 to +3. So our bias is going to be 3, okay? Because we go from 6. So the range 1 through 6 is now going to cover the range -2 to +3. We just kind of shift our values 1 through 6 down 3 spaces to go from -2 to +3. Okay, so our exponent bias still follows the same rules. We're using 3 bits for the exponent, so our bias is going to be 2 to the n-1, 2 to the 2, which is 4, -1, so our bias is 3. Okay, so in binary, we go from 0, 0, 0 to 1, 1, 1, and with the bias, we can go from, I guess, -3 to +4, but all zeros is a special case, all ones is a special case, and so our exponents can go anywhere from -2 to +3. Okay, and then the remaining bits are for the mantissa. We always assume there's a leading 1, so the 4 remaining bits will basically fill in 1 point blank, 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 blank times 2 to the exponent. All right, so the 4 bits that we store for the mantissa go fill in these spots right here. Okay, so let's break this down and try this out. So what if we have these 8 bits here? And I say, what number does this represent? So our sign bit is a 0. Our 3 exponent bits are 1, 0, 1. And our fraction is 0, 1, 1, 1. Okay, so this is what we have. The sign bit's a 0, so we have a positive number. Our exponent bits are 1, 0, 1. Okay, what is 1, 0, 1? If we go from binary to decimal, what is the number 1, 0, 1? So this is the 1's place, the 2's place, and the 4's place. So I have 1, 4, and 1, 1, so that makes 5, right? Okay, so 1, 0, 1 is going to be a 5, and remember, there is a bias of 3. So the values 1 through 5, or 1 through 6 got shifted down to -2 to +3. So that number 5 gets shifted down to 2, okay? So our exponent value, so in 1, 0, 1 in binary is 5, the exponent bias is 3, the exponent value is then going to be 2. So if I kind of go back a few slides to this table, again, our binary bits, these are all of the different representations we have. So 1, 0, 1 becomes 5, but then again, we shift everything down 3 so that basically half our values are positive, 1 is a 0, and then the rest are negative, and so the 5 gets shifted down to a 2. Okay, so our exponent is 5, exponent is 2, and then what is our mantissa bits? Our mantissa bits are 0, 1, 1, 1, and so we plug that into 1 point blank, 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 so we have 1.0111. It's a positive number, and our exponent is 2, so times 2 to the 2. Okay, so what is this? I have 1 point, this is a quarter, an eighth, and a 16th. So I don't know what that is. 1 quarter plus 1 eighth plus 1 16th. So 4 plus 2 plus 1, so 7/16. 1 and 7/16 times 4 would give me 4 and 7/4. 4 and 7/4. 7/4 is 1 and 3/4. So 2.75, 2 and 3/4, I think. I'm doing this in my head here. Sorry, 4 plus 1 and 3/4. Okay, so this is what we have. 1 plus 0 halves, 1/4, 1/8, 1/16 times 2 to this times 4. So we get 4 plus 1 plus 1/2 plus 1/4, and that gives me 5 and 3/4. And this is our value there. Okay, is that all right? Going from this into 5 and 3/4. Okay, all right. So that's what we have. All right. What about this? Let's say we want to represent 2 1/4 in binary with the mini floating point system. So first, we're going to convert 2 1/4 into binary. So 2 becomes 1 0, and 1/4 becomes 0.01. Okay. And then we have to convert this into scientific binary. So we shift everything over. We shift the binary point over to the left. And so now I'm going to get 1.001 times 2 to the 1. Okay, and so the mantissa, I'm going to store 001 into my mantissa as 0010. Okay, so the mantissa will be just this part, 0010. The sign bit is 0 for positive, and then my exponent, now I need to store the number 1 as an exponent, okay? So if I'm putting in 1, I have to apply the bias. I have to shift it back by applying the bias of 3. So now what the number I need to store is the number 4 in decimal. So the number 4 in decimal is going to be 100. So 4 in binary is going to be 100. So our number in binary, 0 for the sign, 100 for the exponent, and 0010 for the mantissa bits. And this is going to be how we store a number in our floating point. Yes? Why do we have a trailing 0? Because we have 4 bits for the mantissa, and so even though we only needed 3 to represent this number, we just have to kind of fill in everything that's left over. So it's kind of like if you wanted to store the number 0.2, okay, but you have to fill in 5 decimal places. You would write, 0.20000 or whatever. You just add kind of trailing zeros to fill in the spaces. And that's what we have. Okay, let me give you your third view quiz answer, which is the letter E. E as in elephant. E is your third view quiz answer. Okay, so we will wrap this up for here. We'll continue this lecture on Friday, where I'll get into represent the number 0, a bunch of other things regarding the floating point system, and then we'll also see you Wednesday for the midterm. So good luck as you study for that. Be on the lookout for a seating chart, and we'll see you Wednesday.